Hey everyone, so in this chapter we're going to be going over the basic elements of scheduling. Scheduling is really important in daily life, such as project management and system development. So let's look at the system development life cycle that we see here below. So the first thing we're going to do, let's say we're building a house. We're going to plan. We're going to make a plan to build the house. We're going to have just like where we're going to go buy where we're going to put the house, what kind of house it's going to be. We're going to analyze what's actually needed. So what are the components that we need for this house? And then we're going to go a little further and use that analysis to actually design. So pick out what features we're going to put into the house. The implementation in this example is going to be us actually building the house. So we're actually going to sit there and use what we planned, analyzed, and designed, and we're going to build it and create the house. After we've created the house, we need to maintain it. That maintenance could be maybe now we need to change something or move something around, and that could be going back to the planning stage. And then we're going to plan, analyze, design, and implement, and it's a full cycle. So we're constantly managing this project of building a house and maintaining it. It could be home improvement projects, and it continues this cycle. So we can see this in a lot of different projects. The NC State building program, space station program, planning a wedding even. You can use scheduling because you have a lot of things that go into that. So we're going to talk a little bit about the vocabulary. One of the biggest things we need to know is the processors, the people that are actually carrying out the work. We're going to use in this chapter the notation with an N. So N is going to tell us how many processors we have. So for example, if we see N equals 2, that means we have 2 processors or 2 people that are doing the work that we can split it up between. If we have N equals 4, that means we have 4 processors. Then the next thing we have is the tasks. The tasks are the jobs or the things that actually need to be done. It's an individual unit of work that cannot be broken down into smaller units. So let's say, for example, we're making a cake. If we're baking a cake, the first thing we need to do is gather the ingredients, and we got to put them all together, and then we have to mix them and put them in the pan. So we can't break down mixing the ingredients together into anything more than mixing the ingredients. So that's one task that one person can be working on. So now we're going to move on to the way that we notate whether we can do something or not. So if something is ineligible, that means we can't do it yet. It means we have to do something else before we get there. So in the example of making a cake, we can't put the cake in the oven until we've gotten the ingredients, mixed them, and put it in the pan, and then we can put it in the oven. So that putting the cake in the oven, A, is not able to be done yet, so we're not going to circle it. Once we've mixed everything, we put it in the pan, we're ready to put it in the oven, so we're going to circle it. It means that we can put it in the oven, or we could go do something else like clean the dishes or something. Then when it's in execution, we put one line across it, meaning that we're starting to put it in the oven. Somebody's picked up the pan and is about to open the oven and put it in there. And then once they actually do put it in there and close the oven, we have completed the task of putting the cake into the oven. So that is our actual task. Now we're going to have processing times that are going to be assigned to each of these tasks. So the processing time is the amount of time without interruption required by one processor to execute X. So how long does it take to pick up the pan and put it into the oven and then close the oven? That is the processing time of putting the cake into the oven. So we're going to denote this by having our letter. So let's say, for example, we have the letter A, and then how long it takes for us to put that cake into the oven. Let's say it takes 30 seconds. So we're going to have A30 would be our time there. It could be minutes, hours, days, or any unit of time. In this, it really doesn't take that long. All right, so now we're going to go over precedence relations. So we have formal restrictions on the order in which the task can be executed, meaning we can't put the cake in the oven until after we've mixed the ingredients and poured it into the pan. So pouring it into the pan and mixing the ingredients, gathering the ingredients, all of that precedes or comes before we can put the cake into the oven. So let's look at a couple of examples. So the precedence relation can be conveniently abbreviated by putting an arrow or an arc. We're going to have X to Y, meaning we have to do X before we can do Y. So X precedes Y. Y is dependent on X, means that if we haven't done X, then we can't do Y yet. All right, the next thing we have is if we have two tasks that don't have any relation. So we could turn the oven on, or we could gather our ingredients. It doesn't matter which one we do first. We could do either of them at the same time. So they are considered to be independent. There's no arrow that is connecting the two of them. All right, the next thing we have is, let's say we have X to Y and then Y to Z. So if we're baking a cake, we have to get the ingredients out of the fridge or the pantry, then we have to mix them, and then we can pour them into the pan. So let's say this right here is getting our ingredients. I'm going to abbreviate here. And this right here is mixing our ingredients. And this is pour in the pan. So we can't mix our ingredients until we get them, and we can't pour it in the pan until we mix them. But by the transitive property, we can't pour it in the pan until we've gotten the ingredients. It's impossible. We have to do all of the things that come before it, all of the precedence relations before we get to the other one. Meaning that X arrow Z, or X precedes Z. Another thing is we can't have a cycle when it comes to a scheduling observation. So if we have X, Y, Z, W, and we have to do X before we do Y, Y before we do Z, Z before W, and then W before X, we'll never get anywhere, because it's like the chicken or the egg, which came first. We don't know. It's logically impossible. So we can't have a cycle when it comes to scheduling. All right, so now we're going to talk about a way that we represent, how do we visualize which processor is doing which task and in what order, and how long does it actually take to finish this. So we have the Gantt charts. A Gantt chart is basically just what you see right here. So it's going to be a timeline. So we're going to have time of some units here, and we're going to have our number of processors. So this right here is our N. So if we have two processors here, because we have 1 and 2. Now if we had a piece of 3 down here, then we would have 3 processors. These are our tasks. So we have A, B, C, and D, and we have a little bit of idle time, which we'll go over in a minute what it means. A takes 4 minutes. B takes 5 minutes. What this is saying is processor 1, so the first person, is performing task A, while the second person has already started task B. Then once processor 1 finishes A, they start on D, and processor 2 starts on C afterwards. And then at the very end, processor 1 is just sitting there waiting until processor 2 finishes that last job, and our finishing time takes 12 minutes. So imagine you just wrecked your car, and the garage is operated by 2 processors or 2 mechanics, and the repairs can be done in 4 different things that we need to do. So the 4 things we need to do is the exterior body work, which will take 4 hours. We have some engine repairs that need to be done, which is 5 hours. Painting and exterior finish work, which is 7 hours. And then repairing the transmission, which is 3 hours. The only thing that we really care about that we can't do before something else is we obviously can't paint the exterior if we haven't done the exterior body work yet. So A is before C. So we can't do C until we've done A. So let's look at Schedule A. So this is a way to do it, but it's really inefficient because it takes 12 units of time here, 12 hours. So we could do A, B, C, D, and then we have all of this idle time right here, which is kind of pointless. So let's see if we can rearrange it a little bit better to make it a little bit quicker. So under this schedule, the project's finishing time is at the very end when both people are finished. So processor 1 finished at 7 hours, but then they're just sitting around and waiting for the rest of these hours until we get to this 12-hour mark. So we're paying the mechanic to sit there for their time when they could get it done quicker. So let's try it a little different. What happens if we shift and we take C and let's just switch these around? So if we switch these around, let's switch here. So what happens if we take C and we move C down here? Well, we can't do that because didn't we say we have to finish all of the exterior body work before we can start painting the exterior? So this little overlap right here can't work. So what happens if we just push it this way a little bit. So we just make a little bit of idle time. Once they finish D, we're going to give them a little bit of idle time. All right, now our finishing time is at 11 hours, which in this case, it's actually the optimal time. We can't do any better. No matter how we shift them around, we're going to have that little bit of idle time there. So we call this the optimal finishing time. Now, if you notice, up until now, we've used the abbreviation FIN for finishing time. And now we're going to use optimal finishing time is going to be abbreviated as OPT. So this is our optimal finishing time, which is the same as fin. It's just now this is our optimal. This is what we want. We can't do it any quicker. We'll get into why when we go to critical path algorithms. So now we're going to calculate the minimum time for it to be completed. Now, the minimum time does not care about precedence relations. This is just theoretical. So if we have a 4-hour, a 3-hour, a 5-hour, and a 7-hour, and we have 2 people working on it, we're going to take our total processing time. So we're going to take the 4 plus 5 plus 3 plus 7. And then we're going to do the number of processors. So we have 2 processors, and that's going to give us our minimum time required. So the minimum time required here, we have to have it as a whole number, so we're going to round up. So we have 19 divided by 2. So we're going to have 9.5, which would mean we need about 10 hours or 9.5 for each one. So what happens if we started adding processors? Do you think it's going to get any quicker if we maybe now have 3 people to work on it instead of 2? So with 2 people, we had an optimal, minimum processing time of 9.5 with only 3 hours of idle time. So there was our 1, 2, 3 hours of idle time. And then we have with 3 processors, we have 19 divided by 3. Well, that gives us our minimum processing time of 6.33, but now we have 14 hours of idle time, then 25 and 36. So we're not adding anything better because we can't really get any faster. So what is the actual minimum time that we could do? Well, we kind of already saw that. The minimum time we could have is 11 hours. And why is that? Let's kind of look into that. Well, we know A has to come before C. So we're always going to have A for 4 hours.